a fact that not everybody appreciates is that for all intents and purposes, continuous Lie groups have been classified, simple Lie groups. And the basic structure of the classification is that there are 4 infinite families consisting of special unitary groups, special orthogonal groups, and the symplectic groups. And then there's also sort of 5 exceptional cases, E6, E7, E8, F4, and G2. And sort of every group on this list appears somewhere in physics, and even the exceptional cases appear quite prominently in string theory, for example, because E8 times E8 is one of the 2 acceptable gauge groups for heterotic string theory that satisfies anomaly cancellation. On the other hand, finite groups are arguably more elementary. Their definition is shorter, they just require less technology to discuss. And yet, at the same time, they're sort of far more complicated, at least from the point of view of their classification. The classification of finite simple groups took a heroic amount of effort by like 100 mathematicians over the greater part of the past century, which you can compare to the classification of simple Lie groups, which was more or less performed by 2 people over 100 years ago, Cartan and Killing. Despite it being sort of more complicated, the basic structure of the classification is sort of similar to that of the classification of simple Lie groups. There are sort of a few infinite families, and then there are also exceptional cases. So among the infinite families are familiar ones like the cyclic groups of prime order. There are the alternating groups. In the middle here, there are a bunch of groups that are more or less obtained by working with the Lie groups that I mentioned on the previous slide, but sort of, instead of working over complex numbers, working over finite fields. And then there are sort of a zoo of exceptional cases. And the largest one is affectionately referred to as the monster. The monster is sort of large enough that it can house many of the other sporadic groups. And in fact, 20 of the other sporadic groups sort of arise in some way or another inside of the monster, as I've tried to indicate with this chaotic diagram. And just in general, the sporadic groups sort of participate in a very interconnected web with one another. So for me, at least, pictures like this inspire a lot of vague questions, which are all along the lines of like, what the hell are these groups? Why are there 26 of them and not more or less? Why do they have the size that they have? Why are they interrelated as such? And so on and so forth. Now, you can pass to a sort of more tractable set of questions as follows. So the key thing to remember is just that group theory is the abstraction of the study of symmetry. That abstraction is useful because, well, it allows us to sort of study symmetry intrinsically without any reference to any object, any external object which realizes the symmetry. But at the same time, presumably those objects which realize the symmetry are the reasons that we study groups to begin with. So we should sort of try to remember what those objects are after all the smoke is cleared, to the extent that we even knew what they were in the first place. So let me ask the question, what are the finite simple groups, the symmetries of? Just to do a non-exceptional case first, for example, there's this group A5, which is maybe the first non-stupid finite simple group that one encounters. And there's this clean statement that basically A5 is the collection of admissible rotations of the dodecahedron. So a very concrete geometric object that exhibits these symmetries. You can ask an analogous question for the sporadic groups. And here there are some results. I'll give you 3 examples. So the monster group, which I referred to earlier, which is the largest of the exceptional finite simple groups, well, it was first proved to exist when Grice showed that it basically furnishes the symmetries of a really large algebra. An algebra is just basically a vector space with a way to multiply two vectors together to produce a third one. And this algebra turns out to also have an inner product. I like to include pictures wherever possible. I didn't really know how to visualize an algebra. It's a very abstract object. So instead, I just have this picture of this whale, which is Monster the whale from Pinocchio. So the monster group will be played by Monster the whale for the rest of this talk. Another sporadic group which has sort of entered the consciousness of physicists in the past decade, for reasons that I'll try to make clear in a moment, is the Mathieu group, M24. And historically, the first place that it was discovered in was in actually coding theory. It turns out to furnish the symmetries of a classical error correcting code called the Golay code. And so I don't know anything about this, but apparently this is a sort of well-known paper in coding theory, a very historically important paper in coding theory. And just to have a third example, there's another group called the Thompson group, and I've spent some time thinking about it as an undergrad and a grad student. And okay, so here, the first place that it was discovered was as the symmetries of a 248-dimensional lattice. So, okay, so in some sense, this is nice. It certainly answers the question I posed, which is what are the sporadic groups the symmetries of? But on the other hand, it sort of does so in perhaps an unsatisfactory way. Depending on how seriously you take this diagram, well, it sort of suggests that the various sporadic groups are sort of interrelated with one another. And yet, when it comes to the objects that realize those symmetries, I sort of have to, for each different group, I'm forced to consider a completely different object from three totally different corners of the mathematical world. You know, I have to consider an algebra, a code, and a lattice. So a natural question is, can we do better? Can we sort of realize these groups more uniformly as symmetries of one kind of object rather than many different kinds of objects? So the answer to my extremely vague question, I declare, is yes, in some sense. And this is where physics enters, because physics offers us a way to sort of realize these various groups in conformal field theory and string theory inspired setups. So let me go over those three groups again, but this time highlighting how they arise in physics. So I'm going to lie a little bit, but roughly speaking, you can think of the monster group as arising as the symmetries of a string world sheet, which describes strings propagating on a very particular 24-dimensional torus, which is related to the Leech lattice. I'm lying to you a little bit because in reality, you have to consider sort of just the holomorphic part of this theory and perform what's called an asymmetric orbifold, but the details of this won't really matter much for what I want to say to you today. So the monster describes the symmetries of this theory basically in the sense that it preserves the correlation functions of the theory. And a natural question to ask is, you know, I told you 2 slides ago roughly that, you know, the monster was first discovered as the symmetries of some algebra. Does that algebra arise in some way in this physical setup? And the answer is yes. So it turns out that this theory has basically 196,884 dimension 2 operators, which is precisely the dimension of the Grice algebra. And you should think that the sort of abstract algebraic structure of the Grice algebra is just encoding various terms in the OPE between dimension 2 operators. For example, I've shown here that the inner product in the Grice algebra just tells you about the z to the minus 4 coefficient, and the ordinary product tells you about the z to the minus 2 coefficient. Okay, so the next group I mentioned was the Mathieu group. Here we know sort of a little bit less, but we sort of vaguely know that the Mathieu group should in some way arise as the symmetries of sigma model with K3 target. K3 is sort of an example of a 4-dimensional Calabi-Yau manifold, which is a kind of toy manifold on which we study string compactification. Now, the reason we know less is because the words I just told you can't be literally true due to various no-go theorems, which tell us that there's no K3 sigma model which actually has M24 symmetry. And yet there's various pieces of evidence which suggest that in some sense M24 should arise. And so in the sense, Matthew Moonshine is sort of interesting because it gives us an opportunity to ask questions about basic phenomena, like what are the symmetries of quantum gravity. Okay, and then you can also ask an analogous question for Thomson-Moonshine. Here, even less is known about the way the Thomson group arises in physics. The current state of the art is that there have been functions which have been constructed which sort of have the right properties roughly to look like generalized partition functions of some kind of CFT-like theory, which has Thomson symmetry. But the exact theory which realizes these partition functions has not ever been written down. So in some sense, the motivation for my talk today is to do even better than these physical constructions because, well, these physical constructions are nice in that they basically realize the various sporadic groups in conformal field theory settings, but they don't do so in such a way that actually reveals any relationship between the groups. For example, what does string theory on K3 have to do with the monster CFT, which was describing, strings propagating on a 24-dimensional torus? Maybe the answer is something, but it's not really transparent from what I've told you. So we'd like to improve upon the situation just one step further. So one issue that we'll potentially encounter in attempting to do this is that, well, the monster group is really, really big, and accordingly it has sort of an absurdly large number of subgroups. Now, if I'm trying to come up with physical models which realize various of its subgroups as symmetries, there's going to be, some groups I care about, like the Thomson group, for example, and there's going to be other groups that I don't really care about.
Yeah.
Sorry? Okay. So there's going to be groups that we care about and other groups that we don't care about. And so we need some sort of principled way to carve out the space of groups that we care about and get rid of the ones that we don't. So I'm going to propose the following strictly group theoretic notion as particularly relevant to our problem. So the notion is the notion of a monstralizer pair. Okay, and the monstralizer is just sort of a silly word for describing something that's very natural, which is we say that a pair of subgroups G and G twiddle forms a monstralizer if they are just two commuting subgroups inside the monster, which are each other's centralizers. So I remind you that the centralizer of some set S is just all the elements of the monster group that sort of commute with S. So such subgroups are sort of maximal in the sense that if I try to, say, enlarge G, I find that I can't do so without introducing elements which don't commute with G twiddle. So they're sort of as large as can be possible without sacrificing commutivity. Okay, so why do I say that this is a relevant notion? Well, so I said earlier that there's a lot of subgroups in the monster, but relatively few of them actually participate in a monstralizer pair. And yet, sort of many of the sporadic groups, I think most of them are involved in some way or another in a monstralizer. So it sort of does a fairly good job of picking out the groups that we care about. And at the same time, I've presented this as a notion that is relevant to the monster group, but actually, centralizing pairs of subgroups is valid inside any group, not just the monster. And there's historical precedence for considering such pairs of subgroups, and it leads to a lot of natural results in representation theory. Perhaps the most natural one is Schur-Weyl duality. And because sort of a lot of the manipulations that I'm going to be doing in the context of CFT are sort of spiritually similar to Schur-Weyl duality. Let me just briefly take 2 or 3 minutes to remind you of what the statement is. So consider a complex vector space V, which is more or less k copies of n complex dimensional vector space. So this admits actions by 2 groups. One is the symmetric group on k letters. And okay, the words are just that the symmetric group acts by permuting the various copies of Cn. Or if you like equations, I've written the equation there as well. The general linear group, GLN, acts very naturally on Cn. So how do we get it to act on k copies of Cn? Well, we just get it to act diagonally. So sort of one element of GLN acts in the same way on each of the k copies. These 2 actions commute with one another. So that's sort of transparent just from their form. What's less obvious is that actually SK is precisely the centralizer of GLN, and GLN is precisely the centralizer of SK. And that's sort of going to be the crucial fact which makes what I'm about to say next work. So the statement that SK and GLN commute is just the statement that the direct product of them acts on V. Sorry, was there a question?
Okay. I do have a question really quick, although
I
didn't pipe up, which is, you say they centralize each other. Is that within the group GLNK?
Yeah, within the endomorphisms of V, yep.
Okay, thanks.
Thanks. So, right, so these 2 groups commute with one another, and therefore the statement is that there's an action of their direct product on the vector space V. And so we can consider decomposing V into irreducible representations of this direct product. And basically, Schur-Weyl duality is a statement about what this decomposition looks like. So, okay, so I've written the decomposition here. At first glance, it doesn't look like anything has happened. Sort of, okay, I've written V as a direct sum of a tensor product of representations of SK with representations of GLN. That's just standard because representations of a direct product are tensor products of representations. But the statement of Schur-Weyl duality is basically that any irreducible representation of either SK or GLN appears at most 1 time in this decomposition. And so if you'd like, the reason that it's called a duality is because it sort of pairs in a 1-to-1 fashion irreps of SK and irreps of GLN based off of how they appear in this decomposition. So that was maybe an overly abstract discussion. Let me just do a quick example to let it sink in. So I'll consider the case that k equals 2. And you can sort of roughly think that V is describing a vector space of rank 2 tensors. And okay, so if we decompose this with respect to S2 times GLN, then what one finds is that there's 2 irreducible representations which appear in the decomposition. And roughly speaking, one representation consists of all the symmetric tensors, and one representation consists of antisymmetric tensors. So this is just a reflection of the fact that any tensor can be written as the sum of a symmetric piece plus an antisymmetric piece. So the symmetric tensors form an irrep of GLN, but they also form an irrep of S2, which is just the same thing as Z2. What's the irrep of Z2? Well, the Z2 sort of acts by interchanging the 2 indices of the tensor. And if it's symmetric, then, well, that's just the statement that interchanging does nothing. So the first sum end is sort of the trivial rep of Z2. And the second sum end is basically also an irrep of GLN. It consists of the antisymmetric tensors. And this time when we swap the indices, we get that we get an overall minus sign. And so that just corresponds to the only non-trivial irreducible representation of Z2. Okay, so I've introduced a group theoretic notion in the monster, and it's sort of going to be the goal of this talk to realize that group theoretic notion in the context of conformal field theory. And we'll see that in the process of doing this, we'll be very naturally led to an answer to our motivating question, which is, what are the sporadic groups the symmetries of? I guess I should have said, we have answers to that question, but we wanted to do better. We wanted to come up with models for the sporadic groups which sort of betray information about the relationships between them. Actually, I won't quite be working with CFTs. I'll be working with a closely related object called a chiral algebra. And so just to sort of set my notations and conventions, I'm going to spend a few minutes reviewing what those are. But before I move on, maybe I should pause and see if there are any questions. Everybody's probably watching Netflix by now.
Brandon.
Yes.
In that operator product for the monster algebra, you said the Grice product appears in the second term. So what about the higher order terms? Are they known?
Yeah, so, well, the monster CFT has no currents, so there's no z to the -3 term. And then the only term that remains is the z to the -1 term. And I think, well, I don't, so I guess I should say the Grice algebra encodes part of the OP between dimension 2 operators. It's probably known in some abstract sense. I don't know of any concrete expression for the OP that for the term in the OP, which is the z to the -1 term. Yeah. Okay, so if there are no further questions, then I'll briefly now review the definition of a chiral algebra. So the starting point for the definition of a chiral algebra is just the observation that a very special role is played by the holomorphic operators of a 2D conformal field theory. One of the reasons is that by basic complex analysis, one can sort of compute the modes of such a holomorphic operator, and those modes will furnish a sort of infinite dimensional symmetry algebra. And I'll give an example of this in a moment. Furthermore, since the product of a holomorphic operator with another holomorphic operator is again holomorphic, you can sort of consider the space of all such operators in its own right as a sort of consistent truncation of the full operator algebra, which is maybe more manageable, or at least a jumping off point for analyzing the full CFT. And so the space of holomorphic operators is the thing that we're calling the chiral algebra. So the full Hilbert space of a CFT decomposes into representations of basically the space of holomorphic operators and the space of anti-holomorphic operators. And okay, so this, for those who are sort of representation theoretic phobic, this is just the statement that any operator in a CFT can be realized as either a primary or a descendant thereof. So you should think that each of these V alphas are representations of the chiral algebra, which are obtained by applying these modes, which are like lowering operators, to some highest weight state, if you'd like, or a state of lowest conformal dimension. So we should make sure that there actually are holomorphic operators in the theory besides the identity. And there's a universal entry in the chiral algebra of every CFT, which is the stress tensor. So in 2D, well, the stress tensor is sort of just conserved, but in a CFT, it's also traceless. And if you write those two conditions in complex coordinates, then what you find is that the ZZ component of the stress tensor is holomorphic. So it appears in the chiral algebra. So we can consider taking its modes. And in this case, the modes obey what's known as the Virasoro algebra. And earlier I said that the modes will furnish an infinite dimensional symmetry algebra. In this case, you can sort of think of the Ln as implementing conformal transformations that are only locally well-defined. And sort of by standard CFT techniques, the commutation relation of the modes of the stress tensor is sort of the same as the OP of the stress tensor with itself, which I've written down below. Stress tensors will play a sort of distinguished role in this talk, so we'll be returning to this OP shortly. So sort of generically, that's all that there is in the chiral algebra, just a copy of the Virasoro algebra at the whatever the relevant central charge is. But occasionally you can have enhancements of the chiral algebra where additional holomorphic operators populate it. So for example, if you have some kind of global symmetry which is continuous in your theory, then by Noether's theorem, that symmetry will have a corresponding conserved current. And on general grounds, it'll be a dimension 1 operator, which is holomorphic. And it satisfies a sort of universal OPE, which I've reproduced below. And here, the F's are the structure constants of whatever the symmetry group is. And JA are sort of like a basis for the currents, one for each generator of the symmetry group. K is another one of these universal terms, sort of like the central charge in the TTOP, and it's related to anomalies. In this talk, I will be working with theories which don't have any continuous global symmetries. So they won't actually have current algebras like this. But I write this down anyways because some of the techniques and the manipulations that I'll be performing are sort of more familiar in the context of CFTs with currents, so I'll be reviewing it in that context. And then moving on to, and then generalizing away from that. But you should sort of think that it's not going to be any dimension 1 operators in any of the theories that I'll actually be considering today, because they don't have any continuous symmetries. They'll only have discrete symmetries. So, okay, so what's our goal? Our goal is to basically start with the Monstrous CFT and construct new theories out of it that realize various of its subgroups as its symmetries, more or less. So what are the sort of basic tools that allow us to turn one CFT into another? Well, one thing that you can very often do is if you have a CFT with a global symmetry group, let's say that it's discrete and it's non-anomalous, excuse me. Well, then you can gauge it. And in the context of 2D CFT, this process of gauging a discrete symmetry, there's a sort of machine which tells you how to do this, and it's referred to as taking an orbifold. But that language doesn't really matter for us. Now, when working with a full modular invariant CFT, the procedure is sort of complicated. You have to introduce these twisted sectors and things like that. But you can ask what the procedure corresponds to at the level of the chiral algebra. So the concrete question you would ask is, say I have a theory whose chiral algebra is V, and I gauge some global symmetry group G of it. What is the chiral algebra of the resulting orbifolded theory? And in general, the answer to that question is variable, but generically, sort of the piece that's always guaranteed to be there is that you have this VG part of the chiral algebra, which basically just consists of all the operators of the original theory, which are left invariant by the symmetry. So in some sense, a lot of the work on Monstrous moonshine has been related to this. So we won't be talking about it in today's talk. Instead, I'm going to be using another method, which is maybe less well known, but it's called the coset method. So let me now review this coset method. Okay, so what's the motivation for the coset method? So we're used to the idea that you can build a complicated theory out of simpler building blocks. One really beautiful example of this is that is an idea due to Gepner, which is that if you take, say, a sigma model with a Calabi-Yau target, and you specialize it to very special points in its moduli space, well, that theory sometimes can be described as what's basically a tensor product of supersymmetric minimal models. So supersymmetric minimal models are sort of the simplest theories with the right amount of supersymmetry that you can have, and it's sort of surprising that these very complicated Calabi-Yau sigma models are, you know, in special cases, just tensor products of these simpler building blocks. So if you'd like, the method of taking cosets is a way to sort of do the reverse. You start off with a theory and you sort of discover its tensor product constituents. You sort of split it up into pieces. So how should we go about doing this? Well, I mentioned earlier that every Chiral algebra has a stress tensor. So in the least, if we're going to split up a theory into a tensor product of smaller algebras, then each of those pieces should itself have a stress tensor. So what should we be looking for? We should sort of be looking for a decomposition of the original stress tensor of our theory into two other stress tensors of smaller charge, central charge. So what do I mean here? I mean that T and T twiddle should sort of satisfy the universal TT-OPE, though with potentially a different value of central charge, and they should commute with one another. By commute, I mean that the OPE between them is regular. It doesn't have any singular terms in it. Yeah, is there a question? Okay. So I claim that if we are to have a chance at decomposing our theory into a tensor product of smaller theories, we should at least be able to do this. We should at least be able to decompose the stress tensor into a sum of stress tensors of smaller central charge. And the equations that describe this are basically what I've written here. So let me give an example of where you can literally sit at home and do this computation. So consider basically just a free boson, 2 dimensions, which is compact. Well, generically, there aren't that many holomorphic operators, but if you sort of tune the radius of the compact target space to special values, then you get additional holomorphic operators which appear in the theory. For example, if I tune the radius to r equals 1 in some units, then there's an additional holomorphic operator which appears, which is sort of this linear combination of vertex operators. And it has dimension 2. So stress tensors have dimension 2, so we sort of we want additional dimension 2 operators to play with so that we can take linear combinations of them and potentially realize new stress tensors with different values of the central charge. So I claim that if you take the original stress tensor of the theory and you sort of take a linear combination of that with this new operator that appears at r equals 1, you can define 2 additional operators, both of which have central charge 1/2 and commute with one another. Now, central charge 1/2 is a sort of distinguished central charge. It's the central charge of the Ising model. And so this observation, the sketch of the calculation that I just gave, is sort of a signature of the fact that at this special value of the radius, a free boson theory basically splits into two copies of the Ising model. Another place that this method occurs, and which was maybe the first place that it occurred historically, is in the context of current algebras. So I think the previous example maybe illustrated it well enough, but in case you're sort of the generation that was around when this was being done, then maybe this will help with how to think about it. So here the procedure is, you have some symmetry group G, some global symmetry group G, and I told you earlier that whenever you have such a group, the chiral algebra is populated with these currents. And okay, so there's also a natural definition of a stress tensor in such a theory. It's basically this normal ordered product of the various currents. And so in particular, I can find another stress tensor in the theory by picking a subgroup and defining the following little t of z, which is basically just the ordinary stress tensor, but with respect to the smaller subgroup H. And if you'd like, basically what Goddard, Kent, and Olive did is they considered the effect of subtracting off this theory, which is sort of based off of symmetry group H, and examining what was left over. And we'll be doing a similar thing. So I'm going to say that in more detail in a second. Yeah.
Brandon, is there like a unique, is the selection of T unique when you pick for a subgroup? I mean, is there like a matching condition, or like the T that you're subtracting, is it unique per group, per subgroup?
Well, this is the sort of standard Sugawara stress tensor. There are probably other stress tensors in the theory that you could consider subtracting off. But yeah, I would say the most natural little t that you could subtract off is this one that I've written here. Yeah.
All right, fine.
Okay, so far my remarks have just been about decomposing the stress tensor. But sort of at the end of the day, what you want is to build theories which have these stress tensors as their stress tensors. So what can you say? Well, at least these stress tensors sort of generate their own copy of the Virasoro algebra. So if you'd like, if you are able to decompose a stress tensor into two smaller ones, then at least what you have is a tensor product of their corresponding Virasoro algebra sitting inside of V. But you can often do more. So you can often construct larger algebras, W and W twiddle, which include those Virasoro algebras. And okay, so I won't give you the details of how you construct these algebras, but the basic idea is that when you choose W and W twiddle to be as large as possible, while preserving the fact that all the operators in W commute with all the operators in W twiddle, that's what's referred to as a commutant pair. And the reason I've sort of introduced this is because it's arguably a CFT version of something that I said earlier, which is this notion of a centralizing pair of subgroups. So this is a centralizing pair of subalgebras of an operator algebra, basically. And so the way we'll proceed with the monster is we'll start off with the monster CFT, and we'll locate tractable and known subalgebras W, and we'll sort of quotient out W. We'll sort of subtract off W and study the theory which remains, which is what I'm calling W twiddle, in its own right.
Good afternoon. This is Dara Hasegi. I'm calling regarding order number 1.
Okay, so on general grounds, well,
C as in Charlie, 1 G as in George,
sorry.
G as in day, 0 Y. The order was
you're the host. You can mute whoever is speaking.
Z37 in monitor, and that was.
Yeah, sorry, I'm like sleep deprived, so I'm unable to even get through this talk without somebody talking. So. Yeah, that's okay. I'll try and move on. So on general grounds, if you have a tensor product of subalgebras of some algebra V, well, okay. So, excuse me. Okay, sorry. Let me start over. So, okay, I told you this earlier fact that if you have the Hilbert space of a CFT, you can sort of decompose it with respect to the product of the Chiral algebra and the anti-holomorphic Chiral algebra. Well, a very similar thing is true in case you're able to find a pair W and W twiddle. On general grounds, you can sort of decompose V into representations of W and W twiddle. But the key thing for us here is that this decomposition is sort of constrained in a Schur-Weyl-like fashion. One way to say it is that sort of each irreducible representation of W and W twiddle appears at most one time in the above decomposition. So if you'd like, sort of V is formed by taking at most one primary from each of W and W twiddle.
Sorry, Brandon,
Yes.
clarification. So curly V itself is a Virasoro algebra, right?
It's large. So you can imagine that V is the monstrous CFT.
Okay.
It's just whatever the Chiral algebra is. So generically, the Chiral algebra is Virasoro, as you say, but in special cases, the Chiral algebra is sort of populated by more stuff. In general, there could just be more holomorphic operators.
Uh-huh.
And I gave an earlier example of conserved currents in the case that the theory has a global symmetry, but sort of a whole zoo of things can happen. So for example, the monstrous CFT, all the operators are holomorphic. So I can consider it as a chiral algebra, for example.
Good. Okay. Yeah. Yeah. You can have additional currents, in which case. Okay.
Yeah.
Good. Thank you.
Mm-hmm. Okay. So I apologize, that was a little bit technical, but okay, now we can sort of get to the meat of the talk, which is that, okay, so it's clear what our strategy is now. We're going to start off with the monstrous CFT, and we're sort of going to split it up into pieces. And we're going to analyze each of the pieces individually, and we're going to hope that we realize CFTs in the process which have nice sporadic symmetry. I mentioned earlier that the monster group has a lot of subgroups and that we would need some principle to sort of pick out the subgroups that we care about. A sort of similar thing is true at the level of the CFT itself. There's just a ton of ways to cut up the monster CFT into pieces. And intuitively, you should think that the reason for this is that it just has a load of dimension 2 operators, 196,884 of them. And so there are sort of a lot of opportunities for operators in that space to sort of have the OPE of a stress tensor. And so we need some principled way to select certain ways of decomposing the monster as privileged over others. And the way to do this is to remember that the whole reason we're doing this is because we want theories with nice symmetry properties. And so we should sort of select the ways that we cut up the monster CFT based off of how much symmetry they preserve. So, okay, so now let's discuss what happens to the symmetries of the theory when you split it up. So these algebras W and W twiddle inherit some of the symmetries that they have from the monster. For example, let's just say X is some symmetry of the monster. It's just a linear map on this vector space, on the space of states, which satisfies some properties. We can think of X as furnishing a symmetry of, let's say, W, if it sort of factorizes in the form that I've written there. Namely, you should think that, okay, what this is saying is that X sort of only acts on W and its representations while acting trivially on W twiddle. So in the case that we can locate a symmetry of the theory which sort of factorizes in this manner, then we can properly think about it as a symmetry of W. And you can do a similar thing for W twiddle as well. And if you sort of scan over all the possible elements of the monster group and you ask how many of them act on W, how many of them act on W twiddle, well, I'll call MW the sort of group, the subgroup of the monster which acts on W, MW twiddle the subgroup of the monster that acts on W twiddle. And a key thing to note here is that they commute with one another. That's just because, well, based off what I've written up here, the guys in MW sort of act on one tensor factor, the guys on MW twiddle act on another tensor factor, and so they just pass right through each other when you multiply them. So here's the connection with the group theoretic notion I introduced at the beginning of the talk. So if you recall, I considered a pair of subgroups distinguished inside of the monster if they form what's called a monstralizer. That is, if they form a pair of subgroups which centralize each other. Now I've given you a way to attach to every way of cutting up the Monstrous CFT into pieces two commuting subgroups. Intuitively, these two commuting subgroups are sort of the symmetry groups preserved by the decomposition, or if you'd like, they're the symmetry groups inherited by W and W twiddle. And so in the very special case that these two symmetry groups form a monstralizer pair, we'll call this way of cutting up the CFT good. It's like a good way to cut up the CFT, in the sense that it sort of plays maximally well with the symmetry group of the monster. So the basic idea is just that, well, there are tons of ways to cut up the monster CFT, but if we sort of focus on only those ways which play really well with the action of the monster group on the monster CFT, then we're led to far fewer. And it's these decompositions of the monster that we'll be interested in. So let me summarize. We start with the monster CFT. We want to sort of cut it up into pieces. To initiate that program, we tried to locate decomposition of the stress tensor into a sum of two smaller stress tensors. And then we sort of construct theories around those stress tensors. Those stress tensors are the scaffolding, and W twiddle are the house around it. Then we decompose the monster CFT with respect to those two algebras that we found. And we ask ourselves, what symmetries does W inherit? What symmetries does W twiddle inherit? And in the case that those two groups form a special monstralizing pair, then we sort of declare victory. So are there any questions so far? Okay. So so this is very abstract. How do I find a way to cut up the monster CFT?
Brandon, can I ask a big picture question for a second?
Yes, please.
So we're cutting up our monster CFT into these subgroups, and the claim is that these subgroups are somehow going to furnish other consistent chiral algebras, and that these algebras are going to give us like the chiral content of a CFT whose global symmetry is some of the other sporadic groups?
That's exactly right. Yeah, so that's right.
Okay, sorry, I don't mean to steal your thunder, but that's the big picture of what's going on.
No, yeah, that's exactly right. Thanks for re-clarifying that. Yeah, so to repeat, sort of our goal here is to construct new conformal field theories, if you'd like, whose global symmetry groups are these other sporadic groups. And our starting point is the observation that these other sporadic groups often appear as subgroups inside of the monster. And so the way we'll... Yeah, go ahead.
Finish your sentence. Finish your sentence. Please.
And so the way that we'll realize those chiral algebras is by basically splitting up the monster CFT into pieces. And those pieces will inherit subgroups of the monster as their symmetry groups, basically, is the idea.
One question I just wanted to clarify for my knowledge. The monstralizer itself, should I think of the monstralizer as being in the center of the monster group, or is it just simply that elements of the monstralizer commute with each other, but they don't necessarily commute with everything else?
Yeah, they're not in the center.
Okay.
So the two groups are non-abelian for sure.
Mm-hmm.
Or well, sorry, not for sure. They're usually non-abelian. And the statement is just that everything in MW commutes with everything in MW twiddle, and everything in MW twiddle commutes with everything in MW. But they don't need to commute amongst themselves. Yeah.
Okay. All right. Good.
Yeah.
Brandon.
Yes.
The chiral algebra of the monster did not have any currents.
No.
Is that true for all the subgroups you're going to work with?
Yeah, because that's right. Because if they had currents, they'd have continuous symmetry, and sort of all the theories that I'm going to be working with have discrete symmetries. Yeah.
This is true of those Schur-Weyl type subgroups?
Yes. Yeah.
Wow, interesting. Okay, thanks. Yeah.
Mm-hmm.
And sorry, Brandon, one more question.
Yeah.
So the resulting algebras, they're literally subalgebras of the monster chiral algebra?
They're literally subalgebras of the monster chiral algebra. That's right. With smaller central charge.
So they can't have currents because then they would need to have been inherited from currents in the monster, right?
Exactly. Yeah.
Thanks.
Mm-hmm. So, what's sort of the stupidest thing we could do? The stupidest thing we could do is take the stupidest CFT. I'm sorry, I should not speak ill of the Ising model. The Ising model is a beautiful CFT, but it's the easiest one to work with. And so the first thing one might imagine doing is taking the monster CFT and sort of subtracting off the Ising CFT. But okay, first we should make sure that the monster actually has an Ising CFT sitting inside of it. So let me tell you about some facts about the monster that will clarify this. So actually, it turns out that there's a very tight connection between the group theory of the monster and the stress tensors of central charge 1/2 in the monster CFT, which I'll call Ising vectors. So to see this connection, I'm just going to observe that the monster has two conjugacy classes of elements of order 2. One of them is called 2A, the other one's called 2B. And the statement is that there's a one-to-one correspondence between stress tensors and the monster CFT with central charge 1/2 and order 2 elements of the monster group, which belong to the 2A conjugacy class. And I can sort of consider for any such Ising stress tensor, decomposing the stress tensor of the monster CFT and analyzing sort of the other piece that is left over when you subtract off the Ising model. Okay, so I said earlier that if I sort of decompose the monster CFT with respect to W, which in this case is the Ising model, and W twiddle, then I'll get some kind of Schur-Weyl-like decomposition in which every irrep appears at most one time. And the Chiral algebra of the Ising model has sort of 3 representations. There's the vacuum, which has dimension 0. And then there's 2 other representations whose highest weight operators have dimension 1/2 and 1/16. So on general grounds, the decomposition of the monster CFT into Ising plus whatever else remains should look something like this. So I repeat that decomposition up here. So let's think about the symmetries. So the Ising model sort of famously has a Z2 symmetry. And in this context, it's realized in the following manner. So the entire vacuum representation is not acted upon by the Z2 symmetry. And similarly for the representation of highest weight 1/2, all the Z2 does is it sort of flips the sign of all the operators which appear in the highest weight module of conformal dimension 1/16. And if you'd like, what you can do is you can take that Z2 symmetry of the Ising model. If I locate an Ising subalgebra of the monster CFT, I can take its Z2 symmetry and I can lift it to a symmetry of the monster CFT, basically by just looking at that decomposition. And for example, the Z2 acts by doing nothing on the first summand, nothing to the second summand, but acting as -1 on all operators which appear in this third summand, which is Ising 1/16 tensor W twiddle 31/16. So this is the reason why there's a correspondence between Ising conformal vectors and elements of the monster group. The reason is that if I find an Ising stress tensor inside of the monster CFT, the Ising model that it generates has a Z2 symmetry, which can be lifted to a Z2 symmetry of the monster. Okay, and now we're sort of at the punchline, which is now we want to consider what are the symmetries that W twiddle inherits from the monster. W twiddle is just what's left over when you subtract off the Ising CFT. I'm going to rush a little bit here because I don't think the technical details are important. But based off of the discussion that I gave earlier, they should be basically all the symmetries in the monster which commute with that Z2 of the Ising model. And that centralizer has been computed, and it's basically the baby monster group. So in this sense, you should think that the splitting of the monster CFT into Ising tensor baby monster CFT is sort of a CFT uplift of this monstralizer pair, which is Z2 and 2.b. So Z2 is, so why is this a monstralizer? It's a monstralizer because the centralizer of the Z2 is 2.b and the centralizer of 2.b is Z2, basically.
Oh, excuse me, Brendan.
Yes.
Did you say that there are two distinct ways of identifying an Ising, the thing you call Ising zero inside the monster, and that leads to two different decompositions of the form that you wrote?
No, there's many ways of realizing Ising zero inside the monster CFT. Each one leads to a decomposition like the one I wrote above, and each one gives rise to a particular Z2 symmetry in the monster CFT.
Okay, thank you.
Yeah, no problem. Okay, so in my remaining 2 minutes, I should get to the punchline, which is that how do you generalize from here? Well, okay, so I have to rush a little bit. But the basic idea is that there's a class of monstralizers which are basically identified as follows. So the previous example, you can think I sort of took a 2A element of the monster and I considered it a centralizer. Well, now let's take a pair of 2A elements and consider the group generated by this pair. That will be a dihedral group. And let's see, how can I get through the remaining many slides of my talk in the remaining time? So let me just say this. Basically, the way that we generalize away from the previous example is instead of considering just one Ising stress tensor, we consider pairs of Ising stress tensors and consider the algebra that they generate together. And we sort of subtract that off. And the motivation is that there's this tight connection between Ising stress tensors and the group theory of the monster, so we should hope to get something back that's nice. And indeed, you do. So there's several ways to realize pairs of Ising vectors inside of the monster. In particular, there's 9 ways of doing this. And in each case, the theory that you get when you subtract off that pair of Ising vectors is a theory with sporadic group symmetry many times. So for example, there are theories with Thompson symmetry, Fisher 22 symmetry, Harada-Norton symmetry, Fisher 23 symmetry. These are all sporadic groups on the nose. And then there's a variety of other theories that you can get in this way, which are still theories whose automorphism groups are simple, but maybe they're, for example, there's a few that are groups of Lie type, and there's others that are extensions of sporadic groups. So let me just conclude by saying, I'll flash this picture. So in this picture, I've written down a variety of pairs of subgroups of the monster group. And for each of these pairs of subgroups, what we did in this paper is we sort of decomposed the monster CFT into a tensor product of 2 theories. And those 2 theories inherit precisely the symmetry groups that I've listed in this picture. So for example, this entry in the middle here, Z2A and 2.b, that's a pair of subgroups in the monster. And you can attach to it the sort of decomposition of the monster CFT, which is Ising tensor baby monster CFT. And the idea is that those 2 pairs of subgroups are precisely the subgroups of the monster group that the Ising model and the baby monster CFT inherit. And a similar thing is true for all these other pairs of subgroups. But the really remarkable thing is that the CFTs that you get in this manner, they sort of all include into one another in the same way that their corresponding automorphism groups do. So, okay, I don't have a mouse here, so I can't really illustrate this on the diagram. But for example, you see here that the Thompson group, there's this entry D3C Thompson. The Thompson group embeds into the baby monster group. And accordingly, the chiral algebra with Thompson symmetry embeds into the chiral algebra with baby monster symmetry. So somehow the idea is that there's this beautiful diagram of relations between the sporadic groups, which is somewhat mysterious, but it's being mirrored within the theory of vertex operator algebras or chiral algebras in this very beautiful way. Okay, so I was going to go over the computation of some of the characters of the theories, but I think I've run out of time. So I think I've basically made my point, and so maybe I'll open it up to questions if anybody has any. Thanks.
Thank you. Let's try to applaud.
I have an obvious question.
Yes.
So you open the talk with the subgroup inclusion diagram of the different exceptional groups within the monster.
Yeah.
And so the clear question is there some canonical set of symmetries that you think could lead to all of those groups and nothing else? Or is that not the goal, or what would you say your big goal is?
Yeah, so, well, I think the original goal was to try to reproduce this diagram within the theory of chiral algebras. And we sort of partially succeeded in that several of these nodes here, we did find chiral algebras whose symmetry groups are these nodes, and they sort of embed into one another in the same way that these groups do. But this program, I think, of splitting up the monster CFT into pieces is not really going to get all of these cases, I don't think. And the reason is because of this asterisk down here. Not everything is a subgroup of the monster. Occasionally, some of these groups arise as subquotients, which means that they're quotients of subgroups. And sort of this method only really reliably realizes things that are roughly subgroups of the monster as symmetry groups. So I think something else will be needed if one wants to realize chiral algebras whose symmetry groups are all the rest of these groups. But maybe that's a feature and not a bug, because it would be sort of boring if this was the entire story. So there's more opportunity to sort of realize these various arrows in interesting and exotic ways.
Are there some better features of the guys that arise as real subgroups, like the twining functions have extra magical properties or something?
That's a good question. So we haven't done a detailed analysis of the twining functions, but one interesting property of all the theories that arise in this diagram is that their characters all arise from Rademacher series. And for experts in the audience, the ability to realize characters as Rademacher series, Rademacher series don't work in general. They do work in the case of the Monstrous CFT, and you can sort of recover all these twined partition functions, and that's sort of what makes the Monstrous CFT special. So I think the fact that we're able to write all the partition functions of our models using Rademacher series is sort of the first hints that they could be special, but I think we need to do work to actually confirm that.
On the subject of Rademacher and related things, are the partition functions for these guys like they're the coefficient sums of dimensions of ear-eps of the groups, and were those functions known to be modular already?
So yeah, so the characters of these chiral algebras will in general be vector valued modular forms. I think for the most part, most of these new chiral algebras that we constructed, nobody had like written down the corresponding modular forms. We sort of constructed them in several different ways to make sure that we were doing it right. We used Rademacher series, Heck operators, modular linear differential equations. So okay, I'm just because I think it's cute and it's sort of classic in Moonshine to do this, I flash here the characters of the Thompson chiral algebra. And you can see here that the leading coefficients, for example, are precisely dimensions of irreducible representation of the Thompson group on the nose, which sort of verifies our prediction that the theory has Thompson symmetry.
Brandon, sort of piggybacking on Shyam's question, is there a reason why you can't repeat this procedure with some of the sporadic group like the Matthew 24? And because you know how to write down the OPEs for the M24 group as well. And perhaps...
So you mean like starting with the K3,
yeah, exactly.
with the K3 sigma model and doing this?
Exactly, because you said you can't apply this method to those sporadic groups, which are sub-quotients of, of the guy in a monster. So my question is, if you cannot start with groups which you know you can't get out of this particular technique, and then try to recursively build the monster.
Yeah, that's certainly a good question, and I think it's even been brought up before in the context of our collaboration. We haven't pursued that yet, but I think it's a good idea if one wants to sort of realize these other arrows on the diagram that can't be explained by this method. Yeah.
I also just
This is Jeff Harvey. I mean, you're not going to do that starting with a super conformal field theory that's a K3 sigma model, because there is no K3 sigma model that has M24 symmetry.
That's right. Yeah.
But you could sort of imagine decomposing the elliptic genus or something, and well, the elliptic genus somehow witnesses the M24, even if the so I agree it's like way more subtle because of the issue that you mentioned, but
yeah. Just to follow, just another question. There was a paper many years ago by, I think, Matthias Gabriel, etc., by trying to understand that the gravity dual of the Ising model. So assuming there is a holographic, dual for the monster CFT, do you know anything that can be said about the holographic interpretation of the technique that you just wrote down?
I don't know anything besides, I mean, I think a sort of piece, well, these Rademacher series are sort of related to the holographic interpretation.
That's right.
In the sense that the various terms that arise in the Rademacher formula can be thought of as like contributions of saddle points in the bulk path interval in 3D. I think, well, I should say that I think most people don't really believe that I think the earliest thoughts that the monster CFT is holographic were maybe like too optimistic or something.
Yeah.
And I don't know, I don't know, I'm not an expert on that, but maybe Nathan is in the audience, maybe he's not, maybe he can comment. But
yeah, which is why I said assuming it exists. So
yeah.
Okay.
We didn't think about the holographic interpretation, but I think it's a good question.
Sorry, Brandon, can I also piggyback on Shamit's question for a second? So the problem is that some of these subgroups are quotients of subgroups.
Yeah.
Can you get the CFT associated to the subgroup and then like try orbifolding it or something to get the subquotient?
Let's see. So I think in order for that to work, you need some statement like the symmetry group of an orbifold is like a quotient of the original symmetry group.
Yeah.
And I'm not sure off the top of my head if that's true.
Yeah, okay, sorry.
No worries. Yeah, it's a good idea.
All right. If there are no further questions for Brandon, then let's thank him again.
Cool. Thanks.
And yeah, this is the end of the seminar, and hopefully we can do some more meetings in the coming weeks. But
one question, I just want to know, I saw there was an email given out for this thing. Perhaps someone should be sending out emails for all these get-togethers so people know that they're happening. Because if there was like a meeting on Friday, I didn't know there was one.
yeah, but I mean, yes, there is a mailing list now that Steve put.
Okay.
Right, Steve? Or maybe Steve left. Anyway, there is. I can forward it to
Jonathan. Email Steve is the answer to your question.
Okay. Cool. Yeah. Excellent.
All right, guys. Enjoy the rest of the day, and talk to you later.
Thank you.
Thank you, Brandon.
Bye, everybody.
Thank
Thanks.
you, Brandon. Thank you.
Thank you.
Bye-bye.
Bye.
Bye.